Thanks. Well, thanks everyone for joining today. I'm Douglas Salden. I'm a engineer with the Center for Western Weather and Water Extremes here at Scripps, and the lead for the Scripps Technical Forum, where we bring in outside companies to talk about some of the stuff that can further our science that we do. Is also opportunities for speakers from our community to sign up for some of these technical forum talks and talk about what they're working on. But today's talk is by CSignum and their work with electromagnetic field signaling, which harnesses EMFS for wireless data transmission between digital sensors and control systems installed down there in water and in the ground with the world's data networks and computing resources used up here. By transmitting wirelessly through the surface of water, EMFS eliminates cables and their manual alternatives, finally making it possible to optimize what we learn by connecting the oceans with our labs. So today we have Mark Rhodes and David Leslie that's going to be leading us through some of the benefits of EMFS, where it's deployed today and where it's headed in the next few years and its potential impact on Scripps efforts and research. So with that, I'll hand it back to Cannon and she'll talk about some of the Zoom housekeeping.
Thank you, Douglas. All righty, so we are in a webinar format, so please, everybody, feel free to use the Q&A box or the chat. We will save our Q&A discussion till the end after the presentation, but go ahead and add any questions as they come up and we'll cover them at the end, and hopefully we'll have a great discussion with CSignum and our guests. And just a few announcements before we get started. We have 2 more technical forums through this year. Seabird Scientific is coming to campus in October. They'll have a presentation and office hours October 16th and the 17th. And we just confirmed with Teledyne that they will also be coming in person on November 8th. This recording and all other of our technical forum webinars are available online, and please connect with myself, Vanessa Scott, or Douglas about future ideas. We'd love to highlight any Scripps projects or case studies with industries, or if you have a really interesting idea or thing you want to share with the Scripps community, we would love to support you both virtually and in person. So reach out to all of us here at the Technical Forum crew. And with that, I will stop sharing my screen and turn it over to David, Mark, and John to get started with your presentation. Oh, David, we've got you on mute.
I think I did that to myself. My apologies. Is the screen okay? Am I sharing my screen yet?
We don't see it.
Okay. Let's see. So it says, apologies, share. Had to happen. How's that?
There we go.
Okay. I'll be very quick. I am essentially a master of ceremonies here today, although I am going to be stepping in for Dr. Binder. First of all, we are very, very grateful to everyone there for the opportunity for the discussion. Joining me is Mark Rhodes, literally the co-founder and chief technology officer and patent holder for the science that represents what we are turning into commercial products and the use of electromagnetic field signaling. It has been a joy at my age and this point in my career to get to work with Mark. Equally to work with John Fajans, who has a broader background and more experience under the water with more digital things than I can't imagine there's how many people would have more experience than he does. So it's lovely to have him with us. Dr. Binder from Florida International is the technology guy for the Aquarius Reef Bay Habitat. Don't know the familiarity with that or not. Relatively well-known base in the Florida Keys, one of a kind. He is on a Norwegian research ship today, and we were all set to have him. The technology was actually working, but regrettably, nature decided to bring the ice in much sooner than they expected, and it was sort of all hands on deck, not in a dangerous situation, but he can't join us, but I do have his material. I would like to simply share something that I have utilized and thanked Margaret for, and the only time that I've had the opportunity to do that. Oh gosh, around 2 years ago now, after I had reached out to her, there was an email that came to me describing us as intriguing. The way in which, as she was taking on the executive director's role there, how frequently the subject came for her to speak on as this ocean Internet of Things, especially the eye. She noted that most people are focused on the things and very few are focused on the internet. And that's for a very stark reason, which is how do we actually communicate between the things that don't work with cables? And that's a perfect way to think about CSignum and why we have the homepage that says connecting digital assets below the water with the networks and resources above the water that we need to actually have anything remotely similar to the concept of an ocean Internet of Things. So I am going to show you something that we were also very pleased to participate in. This is a movie, but I didn't trust the technology. So I've going to just run through for a few minutes. We were in Newport, Rhode Island, Mark and I, about 4 weeks ago, at the invitation of the Naval Undersea Warfare Center and its relationship with what's known as Blue Tide. This was an innovation event, and so it was a wonderful place for us to go and do some actual demonstrations. This is the sailing club in Newport where we were based. This is an incarnation of our product. An EM2 modem is in the upper right on the right picture. But as it says, this is an inflatable surface recovery system, which does have actual use in river monitoring, et cetera. But is also really the only way for us to demonstrate our product. It's not an easy thing to show people. But this is an EMT modem in a rack with an inflatable CO2 cartridge, in the bag. And just to give you a feel for what happened here, it was fun because we got to stay on the balcony. EM2's on the table there along with the laptop. And if you look out towards that pier, you get a feel for the distance that was happening here. Out on the corner of that pier, there's a bridge, and that is where we put the recovery unit. That's Mark doing the heavy lifting. And into the water it goes. This was 5 meters of water at about 100 meters of distance from the building. We didn't know that we'd have the opportunity to give a personal demo, which we moved over and set up on the pier to one of Rhode Island's only 2 congressmen, Gabe Amo. And Gabe was fascinated, obviously, being in Rhode Island, it was pertinent. So he not only came to understand what it was, but he got to actually drive the demo and push the button. And so, whoops, he was interested to see. He's checking out the water and waiting for it to come up. And indeed, we were thrilled to see. I'm sorry for the flashing. Well, I thought that was okay, but the point of this story is, and now I'm proving that this was not a slick sales presentation. It all floated to the surface in its appropriate 20 seconds. And literally, it was just really fascinating because this just doesn't happen anywhere on our planet in terms of the ability to send wireless data, commands, control, information retrieval from up here, in this case up in the building or out there on the pier, and command that device that's in 5 meters of water to do what we want it to do. So I'm now going to give the stage over to Mr. Rhodes to talk about electromagnetic field signaling. But it is a real product that is in fully shippable commercial manufacturing and ready to go, and in fact on its way to multiple places around the world. So thanks. Mark, you all set? I'm going to stop sharing.
Yeah, thanks, David. Hopefully everyone can see my screen. Is that okay? Is that sharing now?
Yes, we can see your screen. It's not in presentation mode, but we can see it.
Thank you. I think I'll stick with that as if I'm winning. Right. Thanks everybody for coming along. Mark Rhodes. I'd like to briefly explain how the technology works and what our products do. And the really important thing I think is to illustrate some applications that we're finding a great fit for this technology, because what it's really all about is understanding what the physics of what the technology can deliver, and then understanding there are some really compelling applications for it, that really provide some functionality that we think is really key to opening up the instrumentation underwater in general, and it certainly applies to oceanography. So I think everyone's aware that conventional wireless radio doesn't work underwater. Conventional radio is based on radio waves. It doesn't pass through the water to air transition. We all know that acoustic modems provide great performance in the deep ocean, but they can't pass from under the water to above. Similar sort of reason, wave-based comms reflects at the surface. So you have to run a cable from above to below, and really, I think that's really the reason you don't very often see acoustics in shallow water in rivers and at the coastline, because really, if you've got to run a cable to have your acoustic modem in the water, you've really done the hard bit. You've done the transition between above to below, and you may as well carry on to the instrumentation with all its associated problems. So we fill that missing link in the wireless communications deployment. We can go from above the water to below, which is the missing part, which is cabled in acoustic systems, and so deliver a truly wireless link from sort of desktop to seabed by a combination of the appropriate technology in the appropriate place. And we do that with electromagnetic field signaling because it crosses the surface. And because we've realized that there are applications for this technology, and we were first to really realize that, we've got 22 granted patents that we maintain in the area. So it is unique. Sorry, I should have highlighted the product here you saw briefly in David's presentation. It's a very different form factor. It's not the typical sort of cylindrical subsea enclosure you'd see for normal devices. We've gone for this flat form factor very purposefully because it has to close a loop antenna, in fact, a multiple 4 antenna system. And it's this shape so that it's got a low profile, so it can function very well in the surf zone or in rivers, high flow areas. So that this is our EM2 product that you saw briefly in the previous slide demonstration that really illustrated how you could control things from that building in the harbour, really, completely wirelessly. So that's a typical application for us. We would typically attach our EM2 under the water to a sensor or something we want to control, because it's obviously two-way communications, and pass with our electromagnetic field signaling technology from under the water to above. The second one of our EM2 units, the identical product, works above the water, doesn't need to be modified for above water or below. And there we'd either end point for the data by directly connecting to the EM2, or we connect to satellite systems or cellular to access the appropriate sort of long-range backhaul terrestrial comms that we're all familiar with. So this is why we say, with cellular or satellite to EM2, linking to under the water, and then in some cases using acoustics for longer range under the water. We've really got a completely wireless ecosystem, wireless solution. So everyone's seen the benefits of that sort of approach above the water, and we really haven't had it before in the underwater domain. And so we can pass through fresh water, seawater, through a surface of ice. There's no impediment to our signal, and through soil or rock, so we can pass through the seabed. It's a lower loss path than the highly conductive seawater. There are underground applications for that technology. For this technology, I won't highlight them in this talk because it's not the intended audience. But we've found really good applications in wind turbines because they're structures that bridge from underwater to above. Ships, again, the hull bridges from underwater to above, so we can fit devices on the ship hull and communicate to the deck. And river and coastal monitoring, again, the shallow water to the riverbank or surf zone to shore. And this diagram really summarizes all of the application modes that we see for our products. There's installing an EM2 on the riverbed, for example, or in the surf zone on the shore, close to shore. We can communicate straight to the land. Here we can access the cellular network to upload data and put it online remotely. Through ground from storm drains to the surface. That's an easy one for us using this technology. Through ice in the winter. I guess that would be appropriate for what Ben Binder's out doing today. And we've even illustrated communications from drones straight to the seabed in the past. We've done this in a pilot system to illustrate this capability. It's again a unique capability which we got a lot of interest for in Rhode Island in the demonstration for the National Underwater Warfare Center, because it's linking these two domains which really can't be done effectively in any other way. We also can avoid topside installations entirely by having a portable system. The system's small enough to fit in a backpack, and we can query and upload data from units on the seabed on demand, or as we illustrated in the start of the talk, we can control things underwater, so we can cause an airbag to inflate so that the system can be recovered for servicing calibrating sensors without having to enter the water, for example. So we have these two products modified for different applications. The EM2 I've mentioned with its omnidirectional antenna, combining 4 antennas, 1 in transmit and 3 in receive. The acoustic gateway option, where we can connect to an acoustic modem to go longer distance once we're under the water. And we can communicate up to 330 feet range with this product. As the range is dependent on the percentage, the part of the water, the fraction of the water, the communications path that's underwater and that which is above air, in the air. And then the EM2S is the same product packaged differently. This can be welded onto the hull of a ship for hull work. And I'll explain that a bit more in a minute.
Hey, Mark.
Yeah.
I apologize, but in order to have John be able to speak because of the scheduling issues that came up, if we can let him jump in and then you come follow back in behind him. Mark.
So that's, in that case, this is the general description of the technology. And if I have time to come back, I can explain where we've found some really compelling applications for this technology. But at this point, I'll hand over to John Fagins.
Thanks, Mark.
Hello, everyone. Thank you for joining us. My name's John Fagins. I'm the Ocean Coastal Applications Manager for Xylem. I got interested in this EM technology a few years ago, back before CSignum even occurred, when it was originally WFS, and I've really enjoyed working with the team as they've developed the technology into a commercial product. I kind of became an unofficial advisor on how to utilize aquatic applications and apply this technology to those applications. And we started with the YSI EXO sonde, and we've taken that farther now with some additional sensors. I'm not here to promote Xylem products. I'm here to promote this EM technology. So if there's a sensor that goes under the water, there's a high likelihood that we can connect it to this modem and deploy it. I particularly got interested because I see a very significant role for this in getting data out of the water in difficult environments. And Mark has already touched on a number of those. Trying to get current and water quality data from underneath the ice in near real time has been, a significant problem for scientists. They've tried ice buoys, and sometimes they work, sometimes they don't. This technology, I think, is going to significantly improve those capabilities. Again, getting water flow instruments, getting that data through pipes and through the ground to the surface, getting even algorithms that are installed on remotely run things like pigs through pipes that once they reach a blockage, then have to go through a series of onboard algorithms until they can figure out how to work past it, because there's no communication to that device. Now that communication is absolutely viable. I see this as an application that I'll be using frequently to get data from the bottom up to a buoy, particularly in nearshore environments like coral reefs, where inductive modems and cables are expensive, and running wired cables are always the weakest link due to wave action. So I'm very excited about this technology. I've been involved with some of the testing. Mark's going to talk a little bit about some of the testing that we did at the Aquarius habitat down in the Florida Keys, where we successfully demonstrated collecting water quality data from outside the habitat using a device that was on a floating platform that we had suspended from an airbag so that we could try it in different locations. But we were sending that data through the hull of the habitat to a scientist who was seated inside the habitat at a table. And I think that's remarkable. So I just want to thank Mark and David for the opportunity to attend today and make my comments. And if there are any questions for me or my experiences with this technology, if I have to get off this call before it's over, I'm sure they'll forward those questions to me, and I'll be happy to answer them and respond to you. Thank you.
Thank you very much, John. Mark, thanks for your patience with my interruption. Again, John Fagins has an endless array of experiences with digital assets in the water. I've yet to find one that he hasn't had his hands on at some point, and very few of them that aren't actually in his office or his garage somewhere. So a wealth of knowledge we're very fortunate to have. Mark, thanks so much.
Okay. Okay, thanks very much, John, for outlining your experiences with the product. Can everyone see my shared screen?
I can see it.
Yes.
I mean, a few problems with things on the screen. I don't want to be there, but I think we can work with that. Yes, how about that? Yeah, so I can just complete what I was going to explain in the next 10 minutes. So I wanted to just illustrate what electromagnetic field signaling really was. So really it's a much more field-based mechanism than the radio waves that people are used to using for wireless communications. And so I've illustrated here the field lines you'll be familiar with from kind of a bar magnet. And so it's a bit like that. We reverse the polarity of the field at 3 kilohertz and then modulate that to carry out a signal with a lot of clever DSP to overcome the distortion that is introduced by the quite complex channel of dispersive seawater. And also we have to deal with the complex field pattern that this produces. So we tend to use a single transmit antenna, and this slide just quickly illustrates that if you were to use a single receive antenna, then the correct alignment is in line with the field lines. So if you have something that's mobile as it passes through this field, you want to be in this alignment here. But in this position, it's still good on the surface. Sorry, that's my train of thought. In this position, I've illustrated with a red symbol to show that that's a bad place to receive the signal because it's obviously crossing the field lines. So you can see from this brief illustration that you'd really like to change your antenna orientation as you move through the field, and we've done that with the M2 because it uses a multiple antenna system that can arrange in X, Y, and Z axes. So we can automatically combine the signals from these three receive antennas and using combinational DSP and always be optimally aligned effectively. And that's how we deal with mobile applications of things like underwater vehicles moving through this field, or even a very simple, fairly common application like a surface buoy moving through the field. It will drift on the surface from side to side. And you can see that the optimum position for the receive antenna will be vertical in this location directly above the submerged unit, or it will be horizontal as very shortly after that as you drift just a short way along the surface. So I'm going to show you some simulations that we've done using finite element analysis, and so it illustrates the fairly complex field patterns, but we've simplified it by illustrating these green zones where we can communicate very effectively, and then these amber zones where we could communicate out to greater range if we have a particularly low noise conditions, but we don't tend to install at these ranges. We have a user interface that we use for commissioning that ensures you're installing in the green zone, so you've got very robust communications. So if we were to look at a cross section through a typical deployment where we're using an EM2 to attach to instrumentation through its serial data link, just very standard serial instrumentation you're all very familiar with. We can wirelessly communicate to one of our EM2s floating within the buoy on the surface. So we're not relying on a data cable through the anchor chain. This can just be a common sort of garden chain that's much more robust than a data cable trying to go up to the surface. So we remove that failure point. And if this is cross section through air, sea, and seabed, you can see some interesting things from this plot. So the transmitting unit is on the seabed here, and you can see that the signal is attenuated as it goes through the seawater. But it does penetrate the surface very effectively, and you can see that the signal makes it through into the air, so you can effectively see why we can communicate with drones to the seabed. You can see that if you're communicating between two systems deployed on the seabed, we get greater horizontal range than we would vertical, because the seabed is much lower conductivity than the seawater typically. So you get a lot of things illustrated from this simple diagram. So we can, if we were 50 feet deep on the seabed, we can cope with 150-foot radius of drift of the buoy. So that would typically satisfy the sort of amount of chain we'd typically deploy in that sort of scenario. And that's one of the typical applications for us. Another one is on wind turbines. So they bridge from above the water to below. And we've found a lot of applications of interest around this offshore wind turbine application. So we can fit one of the M2s at the transition point, as they call it, where you get access to the tower for servicing. And here we can connect to a satellite link. We've integrated with an Iridium satellite link, so you can access this system from anywhere in the world, obviously. And then we can, with the EM2, communicate from above the water to below. And there we can either opt down to another EM2 connected to sensors fairly close to the base. That's often of interest to look at ADCP data, to look at scarring of the foundations, for example, or look at the water quality around the close vicinity of the turbine. If we want to go further, we can use our acoustic gateway to step off and use acoustic comms, because the water is often deep enough to support good quality acoustic comms. And in a security application, we've actually have a system going out that has an acoustic transponder to aid submarine navigation around the wind turbine arrays. So it's an interesting applications. So it's one of the reasons we want to communicate from the seabed. And partly is to deploy instrumentation and control around the wind turbine, but also to signal when this acoustic transponder is assisting with submarine navigation and to run self-tests on the system to check that it's operational continuously. So the quick simulation, just to show you the sort of range that we can easily deploy. So if we were to install at the top side here, 65 feet above the seawater, we can install 65 meters below, and we can communicate to sensors 100 foot away from the base of the tower using our EMFS technology, or longer range using acoustics. Second really interesting application for us is a structure which bridges from above the water to below, which is a ship. So any of the world's ships have really struggled to retrofit sensors, because it's not easy to deploy a cable down the side of a operational ship. It's far from easy to drill a hole through the hull. So typically you don't really get condition monitoring under the surface of the water for the world's shipping, and you don't see the ship able to sense the area around it as it's traveling through the sea. And that's fundamentally because it's hard to fit sensors under the waterline. Well, our wireless system lets you do that. So we can fit one of our standard EM2s on the deck, and it can communicate with the EM2S, which is this streamlined form factor that looks a bit like an anti-corrosion anode, so that it's easily accepted by the industry. Something they're familiar with fitting to the ship. And that, in this example, it's attached to a small sensor that measures the condition of the bearing on the propeller shaft. Very critical part of the ship's infrastructure, of course, because it keeps the ship moving along, which is pretty fundamental to what it does. And we developed a system in conjunction with Thornton Bearings in Canada to monitor their system in line with the DNV regulations they have to meet. And that's launched as a commercial product, and just an illustration of an ideal application of this technology. But more generally, it lets us retrofit sensing and control systems underwater on a hull. That's a pretty wide application area. You can see from this brief summary of the simulations we're doing, this is the sort of range we're getting out of this system. So if you look at the EM2S mounted close to the prop shaft, we can communicate 90 meters below the surface, 100 meters above. Sorry, I'm reverting to meters. Excuse me. 90 feet below the water line, 100 feet above, and you can see this sort of channeling effect we get from the ferrous nature of the ship hull. So it lets us signal further along the hull than we can underwater. So you can see you've got a lot of flexibility with the way you can attach your topside unit. Just to show you that it's not a marginal system, it's a system that's got lots of signal strength to perform this task very easily. And so another area we're finding a lot of applications is in river water monitoring. So conventionally, this is the sort of system people fit to the riverbank and deploy a sonde down this tube into the water. But it's a little bit it's a system that you then need to leave in the field, basically, with a solar panel and a cellular modem to upload the data and make it available remotely. But what we're doing is we're producing a completely wireless system. We can put this assembly in the riverbed, so it's entirely invisible, doesn't attract any attention. We can fit a second EM2 in a tree somewhere and do our upload from there. And so you get much more flexibility with where you site the topside. We can site that anywhere up to 300 feet away. There's a really big opportunity we're pursuing in the UK, where the government has mandated that we fit 40,000 sensors in our rivers. So you can see a wireless system is going to be really useful to deploy on that sort of scale, and it's going to produce a lot of data, which is probably one of the biggest environmental data sets that's ever been available, which would be interesting to the scientific community. So again, the simulation for that, if we deploy in the bottom of a river, 10 foot deep, we've got this sort of freedom to deploy the topside, 345 foot range. You can usually find something convenient to mount a topside for access to the cellular network for upload. And you're not limited to installing right beside the riverbank. And that's a really big thing for these sort of environmental monitoring applications, because permission of the landowner and adoption is biggest practical problem, not the scientific problem of collecting and measuring the data, which conventional instruments do very well. And a very similar application we've piloted with the IOW Leibniz Institute, you may be aware of, over in northern Germany, where we've been using their system to monitor the littoral zone. So this shows a pilot we did with them last year, where we used a small boat to deploy in the surf zone. So they've been struggling to monitor this littoral zone in the past because they can't use their typical system of putting a surface buoy, which they use in deeper water, because that's carried away in the surf zone the first storm that comes along. So they've struggled to actually effectively monitor the littoral zone, and of course that's you folks will know very well that that's extremely important. It's where the land interacts with the ocean, and where all the pollution comes from that ends up in the Baltic, certainly, through interaction with rivers on the land. So it's a key zone to go monitor, and we can now do it wirelessly. So this boat was deploying on the seabed, and we were able to communicate right up onto the beach, and in fact on top of this cliff. So we have an extended range antenna for this application where we can communicate up to 650 foot away. And it frees them from that surface buoy and lets them move in the strategic direction of monitoring the littoral zone. So in summary, just some applications we've found a lot of traction with, because that's really the key thing to understand about this technology, how it works and also where it can be applied. So we've mentioned ship hull, retrofit sensors and control, wind turbines, just to provide wireless access to the subsea environment, so communications from really desktop to seabed wirelessly. And wireless water quality monitoring and river and coastal, which I've just mentioned. And there are applications we're finding a lot of interest in port monitoring, very similar to the littoral zone. People will often want to monitor things in the shipping channel, for example, so they can't have surface buoys, they result in a lot of collisions. So we can actually monitor the water quality or turbidity or water currents, for example, cross currents in the shipping right in the shipping lane, and relay that through a relay system if necessary, straight to the quayside without any surface equipment. Again, I've mentioned briefly surface buoys, so replacing the data cable, much more reliable system, and we can produce communications independent of sea state, because we're not affected by acoustic noise or aeration that's produced by rough weather. Often it's the most interesting data point, to be aware of what's going on in rough conditions when it's stirring the turbidity, and they're exceptional conditions, and we can communicate very well in those conditions. There's no crossover between acoustic noise and our signaling mechanism. And again, in coral reefs, it's ideal for that application, and it's something we're looking at with Florida International University. David will speak about that in a minute, around their Aquarius habitat. And we can either relay the data to a surface buoy or avoid any topside installation and go and harvest the data with drones or unmanned surface vehicle on demand. And that's the mode we've been discussing with a potential customer, to avoid surface deployments around coral reefs because they're often carried away in storm conditions. We can avoid that and effectively monitor, but periodically recover the data through sending a surface vehicle out to upload the logged data. So that's really all I wanted to outline here, what the product's all about, and some applications we've found, some interesting applications here. So at this point, I'd like to hand over to David Leslie, who can talk a bit about our work with Florida International University on the Aquarius habitat. In fact, John Fagans was involved in some trials there last year as well. I think you mentioned that briefly. Thank you.
Cannon, we can't see the questions, so should we consider moving into a Q&A session now?
I'm looking at right now, and so far I don't see anything in the chat.
We have one question from Bethany in the Q&A box, which Mark, you mentioned a little bit, but hopefully you can go into some more detail about how you compensate for turbulence or changes in the sea state with the device.
Yeah, great question. Thank you. Well, really, because we use electromagnetic field signaling, we're completely independent of sea state. People will be asking that question because they're familiar with acoustics having problems in the rough weather conditions. But we don't have any dependence on acoustic noise that's produced by breaking waves. Waves produce aeration, which is problematic for acoustics because acoustics bounces off every little bubble in an aerated zone. But it's actually just has a very slight effect on us, a positive effect of reducing the average conductivity near the surface. So it's just not any crossover. So the only thing we have to do with rough weather is cope with a rapidly changing angle of buoy. So I mentioned that we have to combine signals from multiple antennas. Well, we've done that in an intelligent way that adapts every frame of data. So it adapts every single frame, so we can cope with the orientation changing very rapidly as a surface buoy would if it was rocking on rough waves in rough conditions. So that's how we covered that. Thank you.
And I did find the question
yeah.
chat. So,
I see there's another question come up on the chat regarding serial protocols. So yes, we have RS-232 and 485 because, of course, that's the most ubiquitous interface for standard conventional subsea instrumentation. And so, yes, that's the that we handle both those protocols. They're the most common. And I've also been asked what is the maximum data rate. So we designed the data rate to be suitable for all the applications I've mentioned. So we do 400 bits per second, which is very similar to acoustic modems that have are quite mature in industry, which is come down to those sort of data rates because it's ideal for metrology, the kind of things that is being done under the water with digital instrumentation. So we tend to upload measurements every half an hour, that sort of time frame, or every 15 minutes in some cases, and just really point measurements of conductivity, pH, dissolved oxygen, all the things you guys are familiar with. And so 400 bits per second is ample for those sort of applications. The technology can do more at shorter range, but it's where we've optimized the product in terms of its size, its power consumption, its data rate, its range, to meet the applications I've mentioned. Yes, size of the product. That's a very good question. I see someone's asked what is the size of the M2 package and what frequency ranges are used. So the square form factor I've showed you, a simple way of explaining it is it's very similar to a pizza box. It's that sort of size. So it's 40 centimeters square and 5 centimeters deep. We use 3 kilohertz because it's the key thing to deal with the high conductivity of seawater is to use low frequencies. It reduces the conductive attenuation of the signal. So that's how we achieve the range we achieve by going low in frequency, and we use 3 kilohertz as our carrier signal. So I don't know if there's any other questions. Maybe I need to scroll down.
Yeah, we have. Oh, Douglas, do you want to go ahead?
Yeah, I was just going to say that there was a follow-on that says about the maximum depth tested and what's the temperature and turbidity performance effects.
Yes, so we don't have any effect with turbidity at all. There's just no mechanism for that having an effect because, for example, we can be buried under the seabed. So in applications in the surf zone, we often get covered by sand. That's no impediment to the signal at all. So yeah, turbidity can be all the way up to being covered by the sand, and it just doesn't affect electromagnetic field signaling. The seawater is probably highly conductive. Seawater is probably the thing we have to overcome, and everything else is easier to transmit through. I see there's another question that says, can the units be meshed to extend range? So I've already mentioned our system that communicates from A to B to C sort of nodes with sort of the one point to let's say the A, B, and our EM2 communicating through EMFs, electromagnetic field signaling, to a B node, which is translating from electromagnetic field to acoustics to extend range, and then acoustics to a purely acoustic modem at the sensor, for example. So that's a sort of basic kind of mesh system. But we have a networking address system in our frame structure. we haven't really done mesh as such because we haven't found the large scale sensor deployments that require it. Most people tend to want a sort of star network. You can imagine if you're deploying on a wind turbine and you want to communicate with several sensors spaced around it, each delivering data every half an hour, well, you can address them in turn in a kind of star network. But there's no reason why the protocol can't support mesh networking. It's an area as our red technology roadmap we move into in the future. We can find interesting applications. Yeah, someone's asked about the battery life in transmit mode. Well, so if I can give you an illustration, with a relatively small battery pack, similar sort of dimensions to the modem. We had a sensor in the harbor in Skarbæk in Denmark for 6 months, uploading data from six measurements from a sonde every 30 minutes. And it was deployed for 6 months. And what that limited, it was really retrieved for other reasons. It wasn't for the end of battery life. So it's a very low power system. In transmit, it transmits just over 20 watts. And in receive, we've done a lot of work to optimize the system to be in constant receive mode at 70 milliwatts. Yeah, I don't know if there are any other questions.
Thank you. Yeah, if there are any other questions, feel free to add them now to the Q&A or the chat.
I can pick up and cover a little more on what's happening at the Aquarius Reef Bay if that is appropriate. So let me try to. Do I get to? Yeah, I'll just say share. Okay. Did I have some success on that? Anybody else see Ben Binder's photo there?
Yes, yeah, we can see.
So again, Ben was extremely sorry that he couldn't join us. He did send me these pictures are from this morning, somewhere off of the coast of Greenland, far enough up to where the ice was disturbing things. And that's part of, they don't have equipment with them, but Ben's very curious to talk with the team there that is working in the ice zone to see. That's also a really interesting area for us because of same thing, the EMF is just really kind of impervious to so many transmittal situations that take other technologies down. But he's out on this particular ship as we speak. But back home in Florida in much warmer water is the Aquarius Reef Bay, which is an underwater habitat that's been through multiple ownership series, multiple owners through a series of assignments for about 30 years or so, but has always really struggled through some interesting challenges. It's a bit of a hotel, and people from all over the world come to do research projects there, typically for a period of a few weeks to maybe a couple of months. Everything that they do in terms of connecting things that's not going to work acoustically or anything going through the surface has to be cabled. And then anytime the seas get a little bit choppy, very low wind rates, they've got to scramble and pull all that in. So they're really anxious to understand what modernizing the research teams and the infrastructure that they have to work with by placing a series of electromagnetic modems around the station, which can be gathered up and transmit through one sort of elevator that takes it up to the surface station. We really look forward to doing some almost networking concepts down there, like the mesh question that was there, as well as utilizing the notion of an acoustic hybrid that allows data that's coming from much farther away to travel in the water on the acoustic signal and then get out of the water on the electromagnetic field signaling. They have a brand new seabed sensor assembly that's in place, and we're currently speccing EM2s into this. They did a lot of work with our EM1 unit, which was much less capable than the EM2, and had some designs that were along these exact same lines, but they were testing ranges and speeds, etc. All of it went quite well, but with the EM2 coming up, then that's going to expand now. So Ben is a little bit, as you saw with John Fajan's, you know, when you have a perspective on having been in the water with cables, with all of the alternatives that people go through, it's absolutely heroic. The notion of ending the use of swivels and jacketed cables and the maintenance routines is something that we're thrilled to see has been quite interesting. So that's really the prepared material that we had. Extremely grateful. Would love to see some more questions, or if anyone had any follow-up, I can make sure that the right folks have the opportunity to speak with you and answer anything at all. We'd love to talk afterwards.
I don't see any more questions, but I want to thank Mark and David and John for this wonderful talk and learning about this new technology. I actually have a question. So you mentioned, you talked about the potential for UK AMP8 and measuring flows, stream flows and things like that. I wondered if you have any active systems right now that you've worked with a customer on.
I think Mark
Sorry,
new, yeah.
Was that stream flows?
Yeah,
river
for
monitoring?
stream flow monitoring, you showed a picture
Yes.
a stream, and I just wondered if you had any active systems operation with that customer.
Yeah, well, we have an active system that we've got as a pilot system of our own, and we're actually due to install a pilot with Severn Trent Water in the UK. And we're also preparing some systems to be installed in Miami, in Florida. There's an assessment of 3 different types of water treatment being carried out down there. And we're instrumenting that up with 6 sensors that are sort of installed before and after the water treatment in the stream to assess the effectiveness of the water treatment. So we only have our own pilot system actually running as of today, but we're on the brink of installing, you know, quite a few pilots that have been accepted by the customer, and they're due to go in the water in the coming months.
That's great, because I mean, for some of the work that I do, we do a lot of stream flow monitoring, and interested in learning more about the technology, seeing how people are deploying it, because you've got a relatively large antenna which you're putting down into the water, and how that's some of the places we're putting the sensors are pretty energetic. So how you keep that from migrating away.
Yes, a lot of the we'll move into a solution that deals with high flow in due course. At the moment, a lot of the UK locations are fairly low flow in the sort of lowlands of the UK, and we're starting off with the deployments that are easier to address with our system, and we have a solution for high flow, but it's, you know, we will need to develop that. So that's very interesting, Douglas. I'll be sure to keep you informed of results from these pilots we're installing.
Sure.
Because we'll very shortly have a lot of materials from these installs in the coming months. By end of the year, we should have some great case studies to let you have a look at.
Great.
Doug, I'm in the Washington, D.C. area, and we're in some conversations with what frankly is, I'm not a veteran of the water world, more from the data communications and networking side, and astonished at the amount of effort that goes into the simple act of collecting data, which is just so taken for granted, you know, up here. Sort of we divide that world up here and down there. It's just incredible. I find multiple papers that describe more than 50% of the budget of so many projects is all about simply literally gathering data in these really hard to reach places. I would love the opportunity for any guidance you could have as conversations with 2,400 active river monitoring projects in the United States right now. The USGS has done a beautiful job of literally a database that anyone in the public can research and find that project and everybody involved with it. I'm curious if Scripps is in any of those, just from the learning curve side of that. Do you know if, maybe a dumb question, maybe it's lots of them or maybe a few?
Well, we're a big user of USGS stage. You're talking about the stage gauge network specifically?
I think so. I mean, they actually have several. This is the database that's 2,385 water quality projects, the overwhelming majority of which, if not all of them, are in rivers and streams,
Sure.
often connected to lakes, et cetera. But if that's of interest to you, I'd be more than happy to also update you on any of those.
Yeah. No, I mean, with the Center for Western Weather and Water Stream, CW3E, we have a lot of our own, we're using data from federal and state agencies as well as that they're collecting, as well as installing our own monitoring systems in various watersheds in the West. To supplement holes in the thing. And as you said, field work is often the most expensive, and part of what we do is we bring a lot of the researchers who may not have had a experience working in the field, give them that opportunity.
Right.
They wanted to come out and see what it takes, just so they have that connection about these numbers that they get flowing to their desktop, what it takes to get there, and some of the idiosyncrasies of acquiring it. But yeah, please keep me informed.
I would love to. Does your group work with monitoring the aquifer and the groundwater, as much as the actual river situation? It's another area that is fascinating to us because of the fact that we transmit through the ground is actually better than through seawater.
Sure. So not necessarily as yet specifically in what we do, but some of our partners might. And I know that, some of the agencies we work with where we're providing river or above ground monitoring, and they're recharging aquifers based upon how their systems work.
Right.
So there could be benefits there.
Okay. Thank you. We're rolling right up on 4 p.m.
Yeah, so thank you so much. I said in the chat, but I'll also share with everybody, we will send the recording out and everyone's contact information so we can have more follow-up discussions afterwards. So thank you so much. And if you have any closing statements.
Gosh, we're just extremely grateful and eager to entertain any questions. It is still very much a matter of introducing the world to the science of electromagnetic field signaling and letting them know that it's possible. There's just been so many restrictions on how anybody doing research gets data from where they want it. Again, if there's anyone who would be willing to talk with me about those issues, it would help us in positioning the product, introducing it in the most efficient way. Very similar, Doug, those comments were very helpful. Thank you. Mark?
Well, thank you guys.
Thank you very much. Very interesting discussion and questions. Appreciate the questions, and anything else we're happy to follow up on. Thanks, guys.
Great. Thank you so much. And we'll see you all at the next technical forum.
Thanks, everybody.
Brilliant.